I think we're all set up now. I want to thank you for coming tonight, and I want to introduce our team. We're the Scrubgrass Wall Climbing Robot Team, and we have Matthew Aldrich, myself, Marty Grewak, Brian Meese, Steve Orizon, Sean Tuxell, and Jonathan Ward. We partnered with the Scrubgrass Power Generating Plant in Kennerdale, Pennsylvania, and it's about 40 minutes from the school. They are a coal waste burning plant, and they provide 85 megawatts of power. There are 2 boilers on the site. Each boiler is made up of, it's a 12 by 12 foot boiler, and it's about 60 feet tall. They are made up of 3-inch diameter tubes that are connected by steel webbing. And the problem with the boilers is that the walls wear away over time due to the extreme heat that they are exposed to. Blowouts can occur, and they result in forced shutdowns, and that is one of the main things that our project is looking at, and decreasing the time that these forced shutdowns take and how often they occur. The goals of our robot is to be a visual first responder in a forced outage prior to scaffolding. The machine will climb as high as 90 feet and return back down to the ground, and will move at a speed of 2 feet per second. It will visually inspect the wall with the ability to pan, tilt, and zoom, and will run safely for 12 continuous hours. Secondary goals of this robot are to quantitatively measure the wall, where the machine will be able to measure the thickness of the wall as the robot climbs the pipes, and will provide a graphical output and numerical data that can be analyzed by the user. And now I'd like to turn it over to Steve to talk about how we are going to power up the wall.
All right, so when we started, we literally had a blank piece of paper. We did a little bit of research and couldn't find much in this area, so we didn't have much to start from. And this is essentially the solution we came up with. So the first thing that we needed to figure out was how we were going to attempt to climb the wall. And first thing first, we needed to stick onto the wall. So we considered a couple of different options. We proposed a vacuum-based solution, magnets, because we're working on a steel wall. My personal favorite, rockets. So then, once we had it adhered to the wall, so that we weren't going to fall off, we now needed to propel ourselves up the wall. And we considered wheel treads, sort of like on a track vehicle, a tether that we would attempt to pull ourselves up, and again, my favorite, rockets. But I was voted down, and so we were left with magnets and wheels. So we did a fusion of the two, and actually put our magnets inside the wheel, and made them rotary. A brief overview of the mechanical specifications of the robot. We're working with a 1/4 horsepower DC gear motor. Just gives us enough power to get up the wall as quickly as we needed to. Getting travel speeds of around 120 feet a minute, a little bit larger than that, which we were very happy with. It goes up the wall pretty quickly. And we have a very light welded aluminum frame. Weight was a big issue because we had limited power, so we needed to get the weight down as much as possible. We kind of went overboard with the wheels. Each one of them has 150 pounds of normal force, sucking each wheel down to the steel plate, so we have an excess of power there. We therefore needed a tool that would actually allow us to then remove the robot from the wall, because at 450 pounds, you just can't pull it off the wall. We tried. You can't do it. And to give a quick visual notification of where a bad spot is, we included a paint can that we can use to mark a nice bright spot on the wall, so that you know, okay, there's a bad spot there. So when we were doing the creation of this, we decided to place the major components first, ones that we knew had to be there, like the visual inspection camera up there, and these two data cameras, and the lasers that they need to function, which Matt will get into later, how that all works. So we placed those objects in our CAD program, and then we went through and put in the secondary parts and pieces, the drivetrain and the axles that allow us to roll up the wall. And then finally we sort of grew the frame in through all these pieces so that we picked up attachment points for each one of them. So let me go into a little bit of detail on some of the componentry. We went through a lot of design iterations on the wheels. We have a few of them up front if you'd like to look at them later. We tried all kinds of different things. We ended up with this bottom center picture. It's a axially mounted magnet. The two plates on each side takes the magnetic flux, conducts it down to the surface of the tube, where it comes back in the other wheel plate and through the magnet again, creating a magnetic circuit essentially. Had the best performance that we could find, particularly pull to weight ratio. So here's the frame. We did everything we could to minimize weight. It's welded aluminum tubing, box tubing, and circular tube. We just tried to do everything we could to reduce the weight on this, got rid of any unnecessary componentry until we had something that was rigid, strong, and light. One of the interesting features about this axle design, we wanted a three-wheel vehicle so that we could accommodate variations in the surface. If the surface was bowed or warped or uneven, we always had 3 points of contact so we didn't lose contact with the wheel. But to do that, the tubes actually wander in and out slightly in the sheet. So we took one wheel and allowed it to slide down the length of the axle while still transmitting torque. And then lastly, the drivetrain. We have all three wheels powered, so we have a single DC gear motor with a belt running to both the front and rear axles. And we used the gear motor so that the system could not backdrive, so that once you put it on the wall and really take the power away, it stays. It doesn't have a tendency to roll back, which only partially worked. It works some of the time, but it's not as consistent as we want. So now I'm going to pass it off to Matt with the sensors.
So the whole point of climbing the wall is to use these sensors to look around. A primary sensor is the pet, looks like R2-D2 up there. He's a pan-tilt zoom camera, and he lets us look all around in color, really high resolution. And the point of that is to give us a qualitative look at how these walls are faring. It lets us see any obvious bad spots, any holes, any kinds of wearing away of the wall. So that is the primary goal, and we succeeded on that. Now, secondarily, we wanted a quantitative measure of the thickness of the wall as we moved in real time, and this was a lot more challenging. Currently at Scrubgrass, they use an ultrasound device with gel on the wall, and they go back and forth, and it takes a lot of time, a lot of man-hours to figure out like the thickness of the wall at different spots. And that's really time-consuming and difficult. We checked out alternatives to this. The first semester, a lot of research was done on these different methods to figure out the thickness of the wall from one side. And we ended up with a laser profile image processing way to do this. Or we're trying to do that at least. This is basically how it works. We have, well, as a side note first, these walls carry water inside. So on the inside of the tubes, there's no corrosion or erosion generally. So we were thinking, if we know that the inside of these tubes are constant and that they're always a perfect sphere or a perfect circle, how about we just look at the outside of the profile of these tubes and placing that on top of the inner thickness, we can tell exactly how thick each of these walls is from just one side without using an ultrasound device. So we have these 3 lasers here, and the whole purpose of the lasers is to make a laser line on the wall that is seen by cameras. And basically, you get a visual of a laser line looking somewhat like this. The top is obviously a good, perfect wall. That's what we want to see. The bottom is a severely corroded wall, and this one would probably fail, and there's a minimal thickness that scrubgrass typically has to repair when it gets to that thickness. And so we would compare, the goal is to compare this perfect wall top there to a defective wall profile. The setup is basically like this. In the other underbelly of the vehicle, there are these cameras, two smaller cameras that look ahead at the lasers making a line on the wall. And that is then run through a series of different types of manipulations, and it's just, we process these images to figure out exactly where the laser line is. So here's a general idea of the, just a diagram of how the program works, or eventually will hopefully work. We acquire an image like these images, and we extract from that the laser line, and the midpoint of the laser line, so we can only we have a line that's only a pixel thick then. And the goal then is to take this line that we've extracted and shift it, or rotate it, or just move it a little bit, so that we know we can put it exactly on top of a perfect template line, and then use that to see pretty much the gaps. And yeah, so the bad spots will show up because it'll show a dip, and there'll be a little variance in where the top good line is compared to where the bad eroded profile is. So then you compare, and then you indicate where you've reached your critical thinness, and then ideally this program will actuate the spray can there, and maybe with a small pause, mark the spot with a spray paint, and then move on and continue to find bad places. Here is really what we have now. We use LabVIEW a lot with a little bit of MATLAB to write this program, and you can see on the left there is there are the 2 images that the camera sees. It's black and white, which allows for just a simpler programming. And you see that, like on the left side, each camera is there. On the right side, you see what somewhat looks like, in these images it doesn't look very good, the profile that is created and extracted. And here, we're running up the wall, and as we scroll to the left of this program, you see we can splice these images together and get a pretty rough profile of the tubes, just through looking at these images and processing it. And you see there's a huge gap there. That's